Good afternoon, or actually not quite yet. Good afternoon Eastern time anyway for me. My name is Hadriel Kaplan. I'm from a company called Acme Packet, which makes session border controllers for the carrier space. And I submitted a presentation into NANOG because they'd asked for presentations about VoIP security, architectures, issues, and analysis from the field. And the reality is most carriers don't want to talk about it, and for a lot of good reasons and some that aren't so good. So as a vendor, I thought that we could represent kind of what's happening out in the community, and from a vendor agnostic viewpoint, of course. And so that's the purpose of this presentation. With 30 minutes, there's only so much you can do on VoIP security. It's a huge topic. There are sessions that go on for days at some conferences, and certainly vendors have tons of slides around it. So there's only really so much I can talk about today, but I guess I want to start with how many people here at least know basics of SIP protocol? Raise your hand. At least know how to spell SIP. Okay. So yeah, about half the room. I've been to NANOG before, and I kind of figured that it's a fairly data-centric meeting in terms of the attendees. So I tried to make this less VoIP specific or telco specific, but some of it just can't be helped. But I guess I'll just get right into it, really. So in terms of the overview, this is sort of your basic agenda. We're going to cover really what the problem is that VoIP carriers are kind of seeing today, or starting to really show up today, the solutions that they've been deploying, and some notes from the field. And this presentation is going to be from a VoIP service provider, large service provider sort of viewpoint, not from an enterprise viewpoint per se, although some of it's also applicable to enterprises. I have about 27 slides in 30 minutes, so I'm going to speak fairly quickly, and I apologize for those who are not native English speakers. It may be a little hard to follow. So sort of a quick marketing overview of VoIP world today from a security perspective. So free peer-to-peer voice is very nice. A lot of people use Skype. They claim some 100 million users, well, 100 million downloads, which probably represents about 1 million users. And but the reality is most people really need to reach wireline and wireless sets. So POTS and cell phones still dominate the planet Earth. Cell phones certainly are not going to go away. Their utility function is far too great to go away. So people still need to reach those devices, and grandma is not going to keep her PC on, if she even has a PC, on all the time. So a peer-to-peer type protocol with software-based solutions on PCs is really only applicable to the kind of people who are in this room, frankly, the geeks. And the rest of us, at least the general consumer market, is not as interested in that. And certainly the enterprise market is not as interested in that. From a carrier and enterprise perspective, obviously VoIP is being deployed in huge quantities today, or a very fast growth rate today, for a lot of different reasons: class 5 replacement, peering, IP-centrics, et cetera, et cetera. There are several standards bodies, for those of you who are in the VoIP space know already. There's the PCMM, the Packet Cable Multimedia Market, which is the cable MSOs. There's IMS tie-span working groups, which have defined more the large carrier telco vision of how SIP and other protocols will interwork for voice services. And not just voice, by the way, it's video, it's all multimedia. And then the MSF, multi-service switching forum. There's some other industry groups as well. But essentially almost every tier 1 to 3, every tier 1, tier 2, tier 3 carrier today is doing VoIP in some basic sense of VoIP, whether it be for what I call a peering or wholesale transport, or whether it be an access, a subscriber type model, or a class 5 replacement. They're all doing it in some way or shape or form. Some of them are only in the research stage. They have been that way for 4 years, and other of them not. So what's the problem that I'm going to address in 30 minutes, which is, again, kind of an unreasonable task? The problem really is that VoIP service is becoming a more prominent target for attack. The service provider infrastructure is very susceptible to attacks. Really, soft switches, proxies, gateways, app servers, they're all software-based platforms in most general applications. They run either on Sun Netras or large Sun boxes, maybe large PC-based platforms. At the end of the day, they're mostly really just software, very easy to attack, as you all well know from the website, from HTTP perspective or email perspective, SMTP perspective. And even the hardware, so-called hardware-based boxes, such as gateways, really have a software component to them as well. They still have either a SIP or an NGCP or HV23 interface that is software-based. It's run in software on a local generalized CPU, and that's really the port that can be attacked very easily. Even the hardware side of them, the DSP side of them, so to speak, the part that converts the VoIP RTP packets to audio on the telephony side and the PSTN side, is still open to attack because DSPs actually have a certain rate at which they can handle RTP packets. And it's not just attacks, it's overloads. In fact, to date, most of the outages so far in the carrier networks have been really overload situations, unexpected overload situations. We'll talk a little bit about that later on. The big problem for these carriers, and one of the reasons they don't want to talk about it much outside of within their own organizations and to their vendors, is that it's a lot more than just loss of revenue when they have a service outage due to attacks. First of all, their customers will defect. They'll get very scared of voice over IP, and that's a big deal for these carriers because they're investing obviously billions of dollars. Secondly, they can get tarnished brand reputation. There are legal responsibility issues, as we've seen recently with 911, where they can get sued if they don't provide 911 service. That one wasn't exactly an attack situation. It was an attack on people's family, but it wasn't an attack that caused 911 outage. That was more of a operational or administrative issue, I should say. So the real problem, though, is that SIP over UDP is open to everyone, and we want it to be, right? We want it to be an open communication medium. There is movement for TLS-based, whether it be over TCP or the DTLS over UDP service for SIP movement going on, but really that's not available by most endpoints today. And if it's not available by endpoints, then carriers don't really care about it that much. They want to move there, but they just don't have much equipment that can do it today. Even when they have TLS support or IPsec support, depending on which flavors you like, that doesn't have anything to do with denial of service attacks. TLS is not a denial of service attack protection mechanism. It's a mechanism for encryption and authentication can provide you some attack protection, but the reality is that people implement those protocols either in software or with a hardware accelerator off the CPU, at which point it's really too late in the multi-stage process instead of equipment. You can already attack it long before it ever has to reach the decryptor chip, essentially. So it doesn't really provide DOS attack protection in any form, depending on how you implement it. IPsec-wise, in the 3GPP world, the third generation partnership program, which originally was in the cell phone side of the planet, which is now being moved into IMS for the wireline side for telcos. IPsec is still in the standards bodies there and has been deployed with the GGSNs for cell phone communication, but is not really being deployed for the wireline. People don't really want to implement IPsec for a number of reasons, the complexity of it per se, and then of course the NAT traversal problems with it. So even though I know there is an extension to use UDP-based encapsulation, so you can get past that. The service provider really rarely knows or limits the source addresses of packets coming in from their subscribers or peering points, mostly because they don't know where they're going to be coming from. They know maybe they'll be from Class Bs or Class Cs or from a certain address range, but they don't want to provision per subscriber which address should be allowed in and which address should not. And even for peering connections, so to speak, which are, from VoIP perspective, are between two VoIP providers, they may know the source addresses, but it's still going to be a range because there's a range of equipment that's talking to them. And of course, it can be spoofed, unless people do what VJ was talking about in AOL, where they try to limit at least with ACLs at the borders, some of those, even if, unicast RPF, which is a pretty huge performance hit on most routers today, there's only so much you can really do to stop spoof attacks. Even with digest authentication, so in SIP, there's this digest authentication mechanism, which is actually fairly commonly used today. It's a very basic type, it's HTTP digest authentication. It's not hard to attack, it has nothing to do with preventing an attack. It's just about some simple, very simple authentication mechanism. And so, again, it's very easy to overload that SIP server, whether it be a soft switch, proxy, you name it. And then, of course, DOS attacks may not bring that server down. A lot of vendors today are talking about how their box is DOS hardened or DOS protected. What they really mean is their box won't crash. It won't reboot just because they get a DOS attack. But the service is still down. You're still flooding their CPU with bogus attempts to make calls, and other legitimate users can't make calls. For the users, that's the same as being down. They don't really care that your box didn't reboot. They only care that they can't make a legitimate phone call or video call or whatever. So the first solution, which happened about 3 years ago, was to centralize the VoIP equipment into a data center, essentially, or one or two data centers, and to put a firewall in front of it. They also implement some router ACLs, very basic router ACLs, to try to stop some simple attacks. But the problem was that DOS attacks and overloads would still flood their internal equipment or flood the firewall, it didn't matter. And so, in fact, it made it a little easier because everything was coming into one point. Much easier to overload a single point than it is multiple distributed points, of course. It also had problems when they tried to use multiple paths outside connectivity to their to their data center, because if the return path couldn't be guaranteed to go through the same firewall, then that firewall couldn't, that which tried to open media holes, has nothing to do with the return path of the media from the other side. And then it's fairly inflexible in terms of design constraints. I think everybody understands that. I don't have to explain it to you. What did firewalls do? And what do they even still do today mostly is they really provide very rudimentary screening of SIP. One of the big issues with deploying firewalls for SIP is that the reverse is really the firewall model, so to speak. The connections, which normally enterprises think of as starting from inside the enterprise going out, so you using your PC for web browsing or email, whatever, would start from the inside going out. In this model, are really coming from the outside coming in. Subscribers making calls into the carrier. So the firewall model really reversed, which meant there was no way for them to always allow people make calls from the outside coming in. You basically had to open up holes. If you open up the hole, the firewall is not doing anything other than stopping people from using other port numbers. So it's really a fairly simplistic, almost trivial method of security. Some of them did have built-in ALGs, application layer gateways, to learn the RTP pinholes. So if you don't know SIP very well, or any of the protocols, NGCP, H323, one of the things they all do is they dynamically assign UDP port numbers for the RTP traffic, the actual media, and RTCP too, the control traffic for it. They dynamically assign those during the call setup stage. So they're not known ahead of time. They're not well-known port numbers ahead of time. And of course, a firewall's primary purpose in life is to block port numbers. So one of the things firewalls had to do very quickly was learn SIP a little bit, enough to open dynamically those pinholes so that the media could actually flow in and out. But again, without that return routing path coming the same direction, they were stuck. And the other interesting point is they had specialized hardware to handle creating those open pinholes, but really that was only used for media and not for signaling. The signaling in the firewalls was still done at the central CPU of the firewall, or maybe distributed CPUs. And that's the actual attack point. Media is not really the attack point. Those UDP port numbers may be, but RTP traffic itself is not seen as a major point of attack today. It's really the SIP or MGCP or H323 ports that can be attacked, because then you can take down the whole service. Forget about the single media call. So people tried to start deploying firewalls at the edge. And actually, I think I have a slide on that. Yeah, sort of the second solution, also about 3 years ago, maybe 2 years ago, they started to put firewalls closer to the borders of their actual data network, so to speak. So it obviously provided a little better protection from simple DOS attacks or even DDoS attacks, because you're dividing the problem space up. So obviously, the more you can segment up the amount of traffic that's coming in that's trying to overload you, the better off you are. Very simplistic, very basic concept, a no-brainer. But they still couldn't stop an overload on the internal SIP infrastructure. In other words, the firewall doesn't have enough SIP intelligence to know that a certain number of calls should only be allowed versus just all SIP traffic. Also, when you add up all those firewalls, even if they're configured as rate-limiting ACLs, if you add up all that traffic at once, the internal infrastructure becomes overloaded very quickly. And of course, it created these routing problems. Even if you tried to put them in line, you couldn't really put them in line because firewalls don't perform that well at the signaling plane, only in the media plane, so to speak. And so you couldn't actually have them in line for every traffic. You had to have them offline, essentially, almost like a DMZ type specific location. And ultimately, the soft switches and gateways were still publicly addressed, so they could still be attacked if you could find a way in that's not through a firewall. And obviously, the more you have of these on the border, the harder it is to control that, make sure that all packets coming in for those traffic would always go through a firewall, and vice versa. You want them coming through a firewall in the reverse path as well. So again, some had built-in parsers to verify SIP packets, even simple parsers just to verify sanity of a packet in terms of the actual ABNF, the ASCII encoding of the SIP packets. But they didn't have any throttles to actually slow it down from overloads. And more importantly, they couldn't tell the good guys from the bad guys, because really the firewall has no true intelligence at the SIP layer. It really only knows that it's a SIP packet, therefore it should be allowed in at a certain rate, let's say, but not that this user is a good SIP user and this user is a bad SIP user. They also didn't provide any screening of the RTP media itself. They simply opened media holes. They didn't actually verify that the media was conforming to what the call was supposed to allow it to do. And of course, they couldn't handle home users' NATs, which is probably that was one of the first applications really for session border controllers, was enabling people to use SIP phones behind their home Linksys or D-Link or any of their local favorite NAT boxes at home. Because, again, for those of you who don't know SIP, Inside of the SIP messages are actual IP addresses for opening the media holes as well as for contact information. And if you're behind a NAT and you're using private addressing, those are all going to be wrong once they make it to the carrier. So somebody has to fix that for you. There are some protocols that are trying to get deployed today to fix that from a protocol perspective, but up till now, really, it's always handled by a session border controller that fixes that for you at the carrier side. In terms of the firewall attacks I'm talking about, I don't know if you can read this slide, but this is really just a generic list of your usual everyday firewall protected attacks. Session border controllers can do this too. These are your generic attack types, and you'll see that I put it down the public names of some of them because those are the public names of the scripts that you can download from about 20 different sites on the web that you can attack somebody with very easily. You don't have to know anything about IP, TCP, anything. SIP, you don't have to know anything about any of those protocols. You just download this little thing. Some of these even have a Windows-based version of the attack tool. Some of them can only run through a Linux-based OS. But in terms of spoofing, certainly. The real problem, though, are these. Because these are the actual attack threats that the carriers are now worried about. They can already protect themselves from the generic HTTP style, or not style, but the same attacks that impacted HTTP and email and other services. Those they've already got a handle on. The ones they don't have a handle on are these. The good thing is you'll see that there aren't that many public tools to test these, which means there aren't that many public tools for people to actually attack them. The only, well, there are a few, but the most well-known one is the Protos test suite from the University of Oulu in Finland, which was just a verification engine, really, to test conformance to SIP in terms of the well-formed packet, essentially. And that's been out for a while now, and there was a CERT advisory about equipment that didn't pass these tests, essentially. It's the easiest way to explain it. So what's happening today? And actually, it's been happening for about 2 years. About 2 years ago, session border controllers started to hit the market. They virtually dominate the VoIP peering role now. And again, by peering role, I mean the inter-carrier connection for VoIP, whether it be wholesale or even between two local subscriber providers that want to exchange VoIP traffic between each other without going through the PSTN. When I say dominate, I mean greater than about 80% of the market at those connection points are all through some session border controller or another, some vendor's session border controller. They're starting to dominate the access role, and by access, I really mean the user, local user, consumer user, subscriber model that a Vonage style, for example, would provide, or an ATT Call Vantage, or any of the ones that are starting to be deployed today. And again, the reason that they dominate that role is, one is for security, and two is for the NAT issue and also inner working problems. And there are about over a dozen vendors that offer some form of session border controller for almost every market, whether it be enterprise market, carrier market, you name it. So what is it? Because we talked about, even the presenter before me talked about a session border controller. Well, and I guess in the most basic terms, I'll break it up into the words themselves for the acronym. So session, meaning real-time interactive communications using SIP, H.323, MGCP, H.248, you name the call control protocol, most of them support them all. Border in terms of an IP to IP network border, whether it be from a service provider to another service provider, or from a service provider to their users. Because even if they own that last mile, that broadband connection, they still can't really trust that user per se. Not to say that the user is malicious, but they can essentially be used as a malicious zombie for a DDoS attack. And then controller, the control part of it. So authentication, authorization, admission, attack protection itself, overload protection, lawful intercept, inner working, protocol fixing, all those things are done by session border controllers today from almost every vendor that makes them. You know, they each have different features, of course, but in general, those are the features that most of them provide. So at the basic level, they control both signaling and the media. And from a SIP perspective, they're called a back-to-back user agent. That's the most common term used for them. For H.323, they're called a back-to-back gateway or back-to-back gateway gatekeeper. For H.248 or MGCP, they're called a back-to-back call agent endpoint. There's a lot of different names for these. Ultimately, though, they really offload some of the work from the proxy or the soft switch or the gatekeeper, whatever it may be. And they provide a lot of non-security benefits, but since this talk's really about security, I'm going to not really talk about those, frankly. So the idea seems simple enough, and you'll probably hear out there that session border controllers have a limited lifespan because they'll be implemented on router blades or on implemented in other boxes. And that people said that about firewalls too, by the way, right? When firewalls first started coming out. And there are router blades that do some basic firewall functionality, but nobody really deploys a router blade as a full-featured firewall for a carrier They do some simple ACLs, certainly, but not a true firewall, because it takes a lot of state, to be honest. Not just special hardware, but a lot of software, too. And that's something that states, certainly state memory is rather limited usually in routers. So, of course, it could be done in a firewall or a router, but only if it had the right hardware and software, just like a Linksys router, for example, could be a core router if it had the right hardware and software. But that's the rub. It doesn't have the right hardware or software. So what's so special about this hardware? Let's just talk about the hardware first. First of all, session border controllers do twice NAT, meaning they NAT both the source and the guest addresses in hardware at line rate. And they do it for thousands and thousands of flows because they do it for the media RTP pinholes themselves. Not many boxes other than session border controllers can do that today in hardware. And of course, for the media, you want to do it as quickly as possible so you don't introduce delay. They also perform UDP-based DOS attack protection in hardware. Most firewalls really provide TCP-based DOS attack protection, not UDP-based DOS attack protection, because most protocols don't run over UDP, except now we do have some. Not to say that there aren't very good protocols that run over UDP, but we're just talking about generically from an importance perspective. And then, of course, they have the ability, at least in hardware, to police tens of hundreds of thousands of those media flows, as well as the signaling flows themselves. And then they can do a lot of other things. They can measure the audio video quality of that RTP because they're in that path and they have special hardware to do that measurement. They can also monitor the RTCP reported values. They can perform 2833 translation. 2833, by the way, is the IETF RFC for doing DTMF, dual tone multi-frequency tones. Those are the buttons you press on your phone that produce those little sounds you hear. Those in SIP land are usually transported in the RTP stream as special RTP packets called 2833 packets. But in H323 side of the planet Earth, or even in a lot of SIP boxes today, they don't support that method for those tones transport. So somebody has to fix that for them because they support it as out-of-band signaling instead of in-band media signaling. And then CALIA, or lawful intercept. I don't usually call lawful intercept a security feature because it's not really security for the provider. It's more about, except for maybe securing them from lawsuits, I guess. But ultimately, really, lawful intercept is usually thrown together with security for some reason, so I threw it in here as well. And that's usually done in hardware as well. For copying both the signaling and the media plane, you have to make a mirror copy of that, send it to a very special box that allows you to collect that function and send it on to the government agencies. So that's the hardware side. What about the software? What's so special about session border controller software? Well, first of all, they're a back-to-back user agent, which is a fairly heavy stack. It means you have to have a full stack on both sides of the trusted or untrusted domain. That means they actually keep some session state, call state essentially. They don't have to, depends on how you configure them, but in general, for the most secure model, you usually configure them for session state to enforce SIP behavior. And then they can do call gapping, which means they can prevent overloads from attacking your infrastructure. There is no deeper packet inspection ability than when you actually, does that 10 mean 10 minutes, or do I get a score of 10? It means 10 minutes, huh? Wow. All right, this will be a very fast 10 minutes, or a very long 10 minutes. So there's no deeper packet inspection ability than being the packet receiver originator, clearly. That is the most deep way you can get. When you actually go through the MIME attachment and actually recreate it, you are doing deep packet inspection. You get a chance to remove headers, modify headers, do all kinds of cool things, which some people think are evil things. But carriers think they're cool because it allows them to control what goes in and out of their network. And then you can do complete topology hiding, and that's the part I'll talk a little bit about very quickly. And again, you can do a lot of other things too, overlapping addresses, attack signatures, fraud protection, etc. So I'm running out of time. I'm going to go quickly through this. So what's twice NAT, and why is that so important? And I know a lot of people think NAT is the mother of all evils in the planet Earth, and it certainly would be if it weren't for the fact that so many people use it and actually provide some very rudimentary but useful security features. So one of the first problems session border controllers solved was how to fix, or peg really, make sure that the path coming in is the same path going out for SIP calls and for the media. Because ultimately they're the ones that are going to be opening those pinholes. The easiest and fastest answer to do that is to replace all the IP addresses on one side with different IP addresses on the other side. Essentially, you can think of this from an enterprise perspective when you have that HTTP proxy box that you have to talk through an HTTP proxy to make web connections outside. It's kind of like that model where you have to talk through a session border controller to reach into the core, and vice versa. To reach out of the core, you have to talk through a session border controller. It is your destination and your source. The cool thing about that, or the very important thing about that, is it actually provides a complete separation in terms of IP addressing and routing of the internal SIP infrastructure, or MGCP, or H248, or H323, whatever. Again, I'm going to talk sort of SIP here, but it can be any of those protocols. Can provide a completely separate internal addressing scheme than it is external, which means you can use a private address space internally, or you can use a public one that you never advertise out, either through BGP or any other routing protocol. That means nobody can attack it. Not only do they not know what those IP addresses are, because the session border controller will replace all those headers as they go in and out, so that you can't even discover what their addresses are, you can't reach those addresses from outside. They're unreachable, even if you knew what their addresses were. And that's the primary security function of a twice NAT feature. So what? Well, the important point is, when a call gets made into your SIP infrastructure, the call can move. It can move around all over the place. It can move at the SIP layer, and it can move at the RTP layer. Firewalls can't handle it because they don't really understand SIP. They're not a full SIP layer. If they have a full SIP stack and they do B2B-way, then ultimately they're a session border controller. If they don't, they're not. So what do they have to do? They need a DMZ. They actually send everything to a default. They also can't guarantee that return path. We talked about that before. So doing that twice NAT also provides some other interesting features. Number one is you always know your packets where they're coming in and going out. So from a security perspective, it provides some very nice spots to look at, I guess is the way to say it, monitor. It also simplifies your IP routing and MPLS infrastructure because your FECs are now those session border controllers addresses. You don't have to worry about all the external addresses or internal addresses. It also means you don't have to advertise them. We talked about that already. And again, really what it provides is that singular point. And it doesn't have to be singular in the sense of your whole network. You usually deploy multiple session border controllers, but that call that comes in or goes out through a session border controller stays at that session border controller. It doesn't move around. And that provides a whole bunch of advantages. So what about router ACLs? A lot of people say, well, I can do some security with router ACLs. No, you can't. It's virtually useless. It's very nice, but the problem is you have to keep port 5060 open to make calls. Just like you have to keep port 1719, 1720 open to make calls for H223 or 2727 for MGCP, etc. That problem is that's the exact port that's going to be attacked. Nobody's going to care about attacking port 6000 unless there's some Microsoft-made product that uses 6000, then people will attack it all the time. But if it's only 5060, that's the one people are going to attack. So you can throttle it, but then you're just providing an easier way to attack. Because if you throttle port 5060, people don't have to send as much traffic to overload it because they'll just overload your throttle, your ACL. So again, it's not as good. And then, of course, for the media side, those are all dynamically discovered ports, dynamically created signal ports for RTP. So as Microsoft has said on their knowledge base since 1999, to establish an outbound net meeting, which happens to use H223, but can do SIP someday too, the firewall must be configured to do the following. It has to pass through primary TCP connections on 522, 389, 1503, 1720, 1731, and it has to pass through secondary UDP connections on everything from 1,000 to 65K, which is about as secure as I guess, nobody. This is not at all secure. What's that, 5? Uh-oh. So, a new security model. So, most firewalls are public device agnostic. Again, the model is reversed for this protocol because the user's on the outside, the untrusted side. Not to say that the inside is fully trusted either, by the way. Most security experts will tell you that the inside should be just as untrusted as the outside of your network. But session border controllers can control both sides of that equation, so they can actually make sure that both sides are really untrusted to some degree. So again, this is reversing that role, whereas session border controllers can actually create a trust relationship with those devices. Here's one example of how they do it. That session border controller is actually the address that you give your endpoints, users, to use as their SIP proxy address or the SIP registrar address. That register message from SIP actually goes to the session border controller, and that session border controller can actually look at the register and make sure that that user gets authorized with a 200 OK response. That means he can discover and learn and use that as a trust relationship for allowing calls or denying calls in the future, something that firewalls don't do. That's just one example. So I have 5 minutes. I will quickly go through some notes from the field. So again, these are kind of generalized. Nobody really wants to talk about their security issues outside of the vendor community and carrier community. Peering notes, the traffic volume is growing, but it's still not that huge really per pop. It's about 1 to 4,000 simultaneous calls average per pop. SIP and H223 are still used. H223 is still a fairly large chunk of the VoIP traffic market, despite what everybody may want to think. And trust me, I'd prefer it weren't the case. It's more complicated to have to support that as a protocol. As somebody earlier pointed out, most dialing plans are still configured statically. There is no enum. It's not to say there isn't any enum, but very few enum services out there. For private enum, even for public enum, it's not used much. TRIP, which was supposed to be this BGP-based, nice interdomain protocol for exchanging phone numbers and reachability, has not been implemented, or actually deployed by very many, and nobody, really. Nobody's deployed it. And then the nice thing is attacks on peering points don't happen very often. First of all, because they allow for a very simple security model, because usually you know exactly what the source addresses are of your peer. Also, SIP is not often done, it is often done over TCP with IPsec, or some TLS is starting to show up today, but mostly still IPsec. And that IPsec is really done by a VPN tunnel box, not native SIP IPsec support. And the nice thing is most people don't know the addresses there, so it's hard for them to attack, and usually they can't attack it anyway because those addresses aren't advertised outside of those two peering connections. From an access perspective, SIP is definitely growing very, very fast. H323, though, is still in existence for enterprise customers because PBXs, most people, 2. I'm down to 2 minutes. This would be a very long 2 minutes. So the traffic volume is booming, but there's a great variance in the traffic volume at different POPs. I guess the average, which is not to say that the bounds of the average are very, very tightly constrained, but the average is about 20K subscribers and 2K simultaneous calls today per POP. But some POPs have 10 times that amount. So there's a great variance in that number. There's still a lot of home user NAT issues. I know people want to do stun, turn, ICE, NSYS, UPnP, and Midcom, and 15 other protocols. They haven't really been deployed. Some SIP endpoints now have stun support, but stun doesn't work through symmetric restricted NATs, which unfortunately are a large portion of the NATs in existence, especially at enterprise customers. So you have to do turn, and there's almost no turn deployments today. And they add a lot of complexities, frankly. So they have a lot of issues. Let me try to go quickly through. Yeah, I'm trying to wrap up. So I guess the good news is there haven't been that many reported attacks, at least, other than overloads, like apartments coming back online, or American Idol. Believe it or not, American Idol is an overload event today, even for the TDM side, which is why they have to publish more and more numbers that go through different POPs to get to them. And then the only widely reported vulnerabilities have really been malformed packet handling to date. And a lot of this is really going to be a marketing issue, because carriers aren't going to want to report them publicly. So again, where to go from here? You need to talk to vendors. You're going to get these slides anyway, so you can go through this. The last piece is just on the test tools. There are some test tools available today already that can do some pretty clever attacks. SIP-P, which is an open source test tool, which wasn't made to do attacks, but can easily be run as an attack tool, can do about 2,500 invites per second, which is about a 9 million busy hour call attempts, which is more than most soft switches can really support. I actually personally wrote an attack tool that does about 25,000 invites a second, which is about 90 million busy hour call attempts, which is more than the US gets. And that's just off this laptop that I'm doing this presentation on with its fast Ethernet interface. It's about the max a fast Ethernet interface can push. 25,000 unique calls generated per second. And I'm not a programmer. That was very simple programming in C++. And again, all the publicly available attack scripts can also fill port 5060. If they can attack using UDP in port 5060, they can fill SIP. And that's the problem. So, any questions? Sorry for the very condensed. There's only so much you can do in 30 minutes. No questions? This answered all your problems. Excellent. I guess we're done then.
Okay, then. Thank you.